I record or not. There we go. Okay, recording. So. This is just something we did in the MDE 61 class. And if you want to see it done, you go to that video. It's right there on the assignments page under MDE 61. Okay. Y equals R of x plus 4 times x minus 3 over x plus 1. Just kind of reviewing what we said last time. I wrote down the steps, although I wrote them down kind of previously, yeah, in an abbreviated fashion. It's like I just coined a new word in the language. Okay. We start by finding zeros in the numerator. Now, this is kind of important. I keep stressing it, and I'm probably going to keep stressing it. So you're going to feel like I'm nagging you. But write things out. Don't just start writing down a bunch of calculations. Okay? Because the thing that I see in pre-calculus students in general is they'll start writing down equations without being real clear on what they're doing. Okay? You want to clarify for yourself what you're doing. So I write down zeros with a numerator. Okay. Numerator equals this. Numerator equals 0 if this. Okay. Now, a lot of people just write down this, if that. They might even write down what they think the zeros are without writing any of this. If you do that, you saved yourself 30 seconds of writing, and you didn't learn as much as you could have. Okay. If you write it out, you're telling yourself what you're doing and thinking about why you're doing it, so you learn it a lot faster and a lot better. So when you get to a test, you don't go screwing it up. Okay, because people are at the stage, where they screw the stuff up. They kind of get it, but they get the wrong thing because they're not focused on what they're doing. Okay, if you focus on what you're doing by writing out what you're doing and writing it out, either in the form I do it or in an equivalent form, but with at least this much detail, you're going to learn it better. And again, you're going to learn more for the time you spend on it. You might spend a little more time, but then when it comes time to prepare for a test, you're pretty well prepared. You just got to do a light review instead of having to go back and really learn it finally for the test. Last minute doesn't work out as well. Okay. Now, y'all appear to be doing pretty well in the course so far. Okay. But you got to do it with less pain if you write stuff out. Anyhow, so I write this out. Numerator equals this. Numerator equals 0 if. Why? Because we're trying to find the zeros in the numerator. Write out the equation. The equation splits into two equations. Okay. People don't want to split equations into two equations. If it's an absolute value equation, they don't do it. They just toss away the absolute value signs. I see that in the majority of pre-calculus students at the end of the course. Okay, you can't be doing that. I'm not real tolerant of that by the time you get to the final. Okay, so write this out, split the equation into two. Understand why it splits. It splits because in order for this product to be 0, one of the factors has to be 0. You can't multiply two things together and get 0 unless at least one of them is 0. That's what it comes down to. Your text calls it, I think, the zero property of multiplication. That's a fairly common term. So you got to know the zero property of multiplication and apply it. So there it is. So you got to know all that in order to get this in a reliable way, especially if these things are a little more complicated than just an x plus this or an x minus that. And sometimes they are. If I threw in an x squared plus 7x minus 3 here, what would you do? So it doesn't look like anything I've ever seen. And you'd freak out. On a test, you say, oh my God, I'm going to die. Okay. No, you're not, but you might not do as well on the test. But if you understand and keep your wits about you and just write out your x squared plus 7x minus 3 here and your x cubed plus 14x minus 45 over here, then you can focus on what you have to do with that x squared plus 7x minus 3. You know, if it set it equal to 0, and you go say, oh yeah, I can do that with a quadratic formula, right? And then you're going to get maybe a couple of zeros out of this term. Okay, point is, if you have this format in your mind and you fixed it in your mind by writing it out every time, and then you get a little bit of a curveball on an exam. If you follow this form, you're probably going to figure out what to do. Okay. I don't throw too many big curveballs in this course, but I'll throw a few just to, separate the A's from the B's. Okay. Or minor curveballs, separate the B's from the C's. Okay. Anyhow, next, you find the zeros in the denominator. Well, the denominator is x plus 1. There's nothing to that. You zero the denominator is x equals -1. And you find the y-intercept. What do I write? The y-intercept when x equals 0. I want to write that out every time when I'm learning this. So I don't keep forgetting that the y-intercept occurs when x equals 0. And so I'll think about why that occurs when x equals 0. It's because every point in the y-intercept projects down to the origin where x equals 0. Okay. So if you keep writing it out, you start putting it together. If you don't write it out in detail, if you just do a bunch of scratches, depends how your mind works. Maybe you put it together, maybe you don't. I think you do it better if you write things out the way you see me write them out, or the way you see Open Math write them out. Okay. If you tell yourself a narrative as you're going through the problem. All right. Anyhow, so you plug in x equals 0, you get y equals -12. Everybody can put x equals 0 here, multiply 4 times -3 and divide by 1, you get -12. Okay, nobody's going to have any problem with that. I don't see anybody have any problem, except knowing when to plug in x equals 0 and knowing what it means when you plug in x equals 0. Okay, tell yourself the narrative. Now that you have that, what have I told you? Well, you might not remember everything I told you last time, but I said the algorithm that I recommend is you draw your vertical dotted lines for the zeros. For x equals -4 and x equals 3, you know how to do that. That assignment I gave you a couple of weekends ago seems to have worked to show you how to make this picture, even if it wasn't explicitly aimed at rational functions. It was aimed at just transformations. Okay, so you do the x equals -4 and x equals 3 dotted lines. And then for the 0 of the denominator, you do a light solid line. That tells you visually that, okay, where this dotted line intersects the x-axis, we're going to have an x-intercept, because that's when the numerator is 0. And the light solid lines where the denominator is 0, that's your asymptote. It's your vertical asymptote. What you have near x equals -1 is a vertically stretched reciprocal x plus 1 function, okay, which is just a vertically shifted reciprocal function, okay. This is, if x is close to 1, then this is close to 5 times -2, which is -10. So this is close to -10 over x plus 1. That's a graph you can construct and you can understand. Okay. Now, whether you understand that or not, that's why you have a vertical asymptote here. And I think understanding that, if you can understand that, is going to be an advantage to you. Okay. If you don't understand it, and just remember, that's a vertical asymptote, and it's got to work. If you've done several of these, it's probably good enough. All right. So I'm not going to test you whether you know why that's a vertical asymptote, except maybe with an extra credit problem or something. All right. So now what do we know? Got a vertical asymptote here. It's got to approach this asymptote either coming up from negative here or coming down from positive on the right-hand side. So it's either going to look like this or like this. Which way does it look? Well, the only way we can get through this point and this point is if it comes up from down here. If it comes down from up here, it looks like this. We'd go through the x-axis here, but we'd never hit this point. And we'd have to go through the x-axis somewhere where we can't, because we can only go through the x-axis at the x-intercepts. All right. So we come up from here, we go through this point, we come up to here. On this side, then this asymptote comes from a reciprocal, it's a plane reciprocal function, okay? Reciprocal toolkit function, shifted and so forth. So the reciprocal function, again, looks like this or like this. We figured out it has to look like this because of what happens on this side with these points. So it's got to look like this on the other side. So it's going to come down here, it's going to go through this point, and then it's going to go on. Now, what's our end behavior? Because we've done everything except the end behavior. For large absolute value of x, if x is a million, big positive number, what have we got? That's pretty much a million, that's pretty much a million, that's pretty much a million. A million divided by a million is 1, leaves us a million. So when x gets big, this gets big. So we draw a little arrow here. And if x is negative a million, well, it's like you got negative a million times negative a million over negative a million. That comes out negative a million. So you got to go down here when you go to the left. Okay, now there's this extra thing. It's the slant asymptote. Okay, I erased that and I'm not going to redo it. We might have talked a little bit last time about how to do it. If you want to see it, just take a look at that part of the MDE 61. But what we do is we just multiply this out. We get x squared plus x minus 12. We do a long division, x plus 1 into x squared minus x minus 12. And we get x minus 12 over x plus 1. 12 over x plus 1 is really tiny when x gets big. So when x gets big, this thing is just close to the graph of y equals x. And that comes right out of the long division. And that's a slant asymptote. And if you know that much, you got a pretty good handle on 70% of everything about rational functions. Okay. So got that on the video. You can look at that when you do a little bit more with rational functions, if you choose to do that. But again, that's not assigned till a week from today. Okay. Find a linear function given point and slope. Everybody remember how to do that? If not, review it. Okay, because I'm going to tell you the things you need to know and the things that are pretty easy and straightforward. I'm not going to go into much detail on. If some things on a little trip here, I might go into detail. But I'm going to give an overview of the kind of things I could ask you. So I could ask you to find a linear equation given the point and slope, given 2 points. Given the intercepts. And given rate of change at a point. Okay. They're given a point and slope. I just make little notes. Actually, I'm not. Except to say, what do you do for rate of change? Well, rate of change is just the slope, and you should know why. Okay. So know why. Rate of change is represented by slope. It's because the rise is the change in y, the run is the change in x, and slope is changing that over changing this. Okay. So go back to those ideas if you haven't incorporated them. If you didn't think of them while you were doing your homework, we'll go back and see how they fit with what you did. be able to do a fundamental triangle. With 2 points. You label the rise, run, and slope. Remember that? Okay. You did, people did pretty well with it. I just want to make sure you're on top of it because it's one of the most important things you learn in this course. And there are things that I'm probably going to do on the test because I've been thinking about what to put on the midterm for several days now. And then finally, wait for it to gel, and finally kind of gelled this morning. In about 20 minutes, I put everything down. I got to develop it into a bunch of problems and put it in the test, but that'll take a few hours. So that should get done by, let's say, Saturday. Okay, so find a triangle for 2 points, label the rise, run, and slope. Difference quotient. Remember the difference quotient? How many don't have any memory of the difference quotient? How many kind of have a memory, but not quite sure what to do with it, right? Okay, it's just a fundamental triangle. Okay, so I'm going to list it here. And I'll even f of x plus h minus f of x over h. I'll even draw a picture. Picture is kind of small, but this is x and this is x plus h. Here's the x point on your graph. Here's the x plus h point on your graph. Here's your fundamental triangle. The run is h. The rise is f of x plus h minus f of x. This is rise, this is run, so this is slope. So the slope of this thing is the difference quotient. Difference quotient is what you use to define the derivative in a calculus course, and that's the whole central topic of the whole first semester of the calculus course. Okay? So that's why it's important. This is pre-calculus. This is something you don't want to stumble over when you get into a calculus course. And even if you don't get into a calculus course, you'll see that difference quotient has a lot of power. Okay. We can use difference quotient to understand some things about polynomial and rational functions. And I'll probably have problems on there that ask you to come up with your polynomial function and then do some difference quotients. Okay. And see what that tells you about the graph. It's pretty neat. Also gives you a big head start when you get to calculus. Okay. Look at the application problems for linear functions. Okay. That's important. Take information. Take information from an applied problem, from the statement of a problem, and put that information on a graph. If you can do that, then knowing how to construct graphs and knowing how to get the graph of a function given certain information, like a linear function given the point and slope or something like that, okay? If you can put your information on a graph, it gives you a way of approaching the solution. Okay, it's probably going to be easier for you than trying to write a function without putting the points on the graph. Okay, if you got the points on the graph, you got a tangible picture, and now you can fit that into the idea of a linear function or quadratic function or polynomial function or whatever. Okay, put stuff on the graph. You got an applied problem. If you got something about a projectile, you know, it's this high after it goes this far, well, that's a point on your graph of a quadratic function. Okay. If you got the information to get the function, then you're way ahead. All right. Okay, now I started talking about linear function. Now I'm talking about more general stuff. For quadratic functions, given the general form y equals a x squared plus bx plus c, find the axis of symmetry. The vertex and zeros, keeping in mind that you might not have any zeros. It's perfectly possible to have a parabola that's above the x-axis. It never passes through the x-axis. You don't have any zeros. Okay. Of course, now you did an assignment on complex zeros. People did pretty well on that assignment as a class. Some people, you know, I think everybody made at least 50% in the assignment. Most people were in the 80, even 90% range on it. Okay. So hopefully you understand that stuff. I think I told you last time, if you don't know how to add, subtract, multiply, and divide complex numbers, you really ought to email me, so I can send you a link to an optional assignment. Okay. It's not difficult, but it takes a little time. Okay. You want to be able to find the vertex form. What's a vertex form? It's the a f of x minus h plus k form for f of x equals x squared, your toolkit squaring function. Okay. I.e., it's y equals a times x minus h squared plus k. And then graph using transformations. Vertically stretched factor A, which if it's negative also reflects on the x-axis. And then your red dot goes to the point HK. In other words, you horizontally shift H units, vertically shift K units. Okay. And the red dot's your vertex. If you find the axis of symmetry vertex of zeros, then you know the vertex form, because H and K are the coordinates of vertex. And A is just the same as the A here. It's coefficient of x squared. Okay, A is the coefficient of x squared in the general form. And if you expand this, you're going to get an x squared minus 2xh plus h squared. Multiply through by A, you're going to get an ax squared plus a bunch of other stuff. So this gives you an ax squared, this gives you an ax squared. So the A is the same both places. So you got that for free. If you got this form, you know what A is. Don't have to do any work. They have to know how to use it to transform it, transform the function. Okay. To transform your toolkit function, you got to know what A, H, and K are. So if I give you this and say, graph it using transformations, what are you going to do? Well, you're going to find all this stuff. Then if you know the vertex, you know H and K. And you're already given A. So you can transform it. And make sure you can do that. You're doing pretty well with that. Make sure you come in ready to do real well with that. Okay. Now, everything I said here applies to quadratic functions, to linear functions, to exponential functions, which you don't have to worry about on this test. Okay, or to polynomial functions. All right, well, if you got an applied function, applied problem, put the stuff on a graph and then figure out where you are with respect to all this other stuff. And practice, just do a lot of problems. Okay. Go back and redo some of the homework problems, think about them again. Go to the half credit page and do some. Okay. All right, so that pretty much covers what you need to know as far as linear and quadratic functions. Now there are details that, you know, I might be able to go into some of the details. We'll see how long it takes to get the rest of this done. But I digress from it to equations. You need to be able to solve linear and quadratic equations. Okay. Now, fundamental linear equations. If I put in numbers for A, B, C, D, E, and H, can you solve this equation? Well, I certainly hope so, because it's really fundamental. Okay. It's really pretty easy. You just use a distributive law, multiply through, add up your numbers, add up your x's. So you reduce to these are Greek letters here because I don't want to use A, B, C, and D, and E, and H. I don't want to go any further into the alphabet because I don't remember it. Okay. Actually, I do. Okay, you reduce it to this form. You're going to have an AX. You're going to have a DX over here. So this thing will actually be A. This will actually be D, but I'm not going to write that out. This is just going to be a number. Then you're going to get that number by multiplying this by this and adding this. And this times this plus this gives you this number. So, and the rest is easy. Everybody, I think, knows how to solve the equation from here. Add things from both sides, subtract things from both sides, multiply, divide. do all that. If you have an equation like this, what do? How many of you immediately thought multiply both sides by the common denominator? Okay. It's got to be a reflex. I've been emphasizing that for 2 months now. Okay, you got a denominator multiplied by it. And let's do a D over E. And that clears your denominators. There's no reason when you have an equation that involves denominators that you got to keep the denominators. Okay. You really don't want to deal with the fractions. You don't have to in an equation. So make sure you get used to that idea. That's basic algebra. This equation is going to give you a linear equation. When you get through, you're going to have a linear equation that reduces down to this form, and it's real easy to solve. This is going to give you a quadratic equation. And if you just do it, you see why. And I'm not going to take the time right now to do it. There are other things we need to do. Okay. What kind of equations think you're going to get with this one? Well, you're going to have to multiply by x plus b times x plus d times x plus f, right? That's a third degree polynomial. So you're going to get a third degree polynomial equation. Now, you know what to do with the linear equation. You know what to do with the quadratic equation. You know what to do with the polynomial equation. Probably not, as far as actually solving it algebraically. But you can graph them. So this is a polynomial. If it is a polynomial equation, you're probably going to need to graph the thing. And use the graph as a guide to figure out an approximate solution. Because most polynomial equations can't be solved by any reasonable method. Okay. Any method that's accessible at this level or even at the calculus level. Although there are approximation methods that you learn, especially if you know calculus. Once you know calculus, it allows you to solve these. Sometimes you can end up with polynomial equations or actually fairly simple situations. Okay. You're not going to see polynomial equations on the test. Except with some sort of instruction that tells you, hint, graph this thing. Okay. I could do that too. I'm not going to do this. Okay, so those are some of the main things you got to know how to do with equations for this test. There's more. You're going to get exponential equations and logarithmic equations in a couple of weeks. Turns out those are pretty easy if you know the rules. Okay, for polynomials, got a polynomial in factor form, what can you do with it? I'm going to say use the zero property multiplication, split it into linear and quadratic equations. Okay. Because any polynomial can be expressed as a product of linear and quadratic factors. That's your fundamental theorem of algebra. You've seen that in the homework. I haven't talked a lot about it because we've been talking about what to do once you have the thing in factor form. Okay, and you've seen many different examples of the factor form. If you have quadratic factors that can't be equal to zero, there are plenty of quadratic expressions that can't be zero. Just like I said earlier, you can have a parabola that's totally above the x-axis or totally below the x-axis. Those factors in a polynomial won't give you zeros. Okay. So use zero property and then find the zeros. Just like what I said when we were talking about the rational function. You had that x plus 4 times x minus 3 equals 0. You split that into x plus 4 equals 0, x minus 3 equals 0. Whatever your factors are, set each one of them equal to 0. You get a different equation, which, if it's linear, is going to give you a 0. If it's quadratic, might or might not give you a 0 or 2. Okay. Find the y-intercept. With the curves for x equals 0, keep reminding you. Long run behavior. Is the same as the leading term. The leading term is your highest power term. Whatever the graph of your highest power term looks like, that's what the polynomial function is going to look like for far away from the x-axis, from the y-axis. Okay, it's going to wiggle in the middle. We've talked about that. So that's how you graph it. If they estimate solutions, you could also estimate the extrema, the relative extrema. They didn't put the word relative in there because polynomials don't have absolute extrema. They go to infinity or negative infinity at the ends. Yeah, but they have relative extrema. So you graph the thing and you estimate the peaks and the valleys. So I can draw a picture of that. If this is your polynomial, then there are your relative extrema. I'll put the word, I'll abbreviate the word relative. The zeros, of course, on the x-axis. And this extremum is one of the zeros. One thing I should have mentioned up here is be careful about multiplicity. Multiplicity of your zeros. And this zero would have multiplicity 2, maybe 4, 6, 8, whatever. But it's an even numbered multiplicity. It'll be at least 2. Another thing that you've been asked in open math that I haven't talked a lot about is the number of turning points. You see that? Is it easy? Pretty easy. Okay. Like, what's the degree of this polynomial? What's the minimum degree this polynomial could have? Anybody want to ask them? Hold up some fingers. Okay. Minimum degree. I see a vote for 5. Oh, now I see a vote for 4. Now I see another 4. Okay, yeah, it's 4. Okay. You know the degree is 4 because its end behavior is the same as both ends. Well, you know it's even because only an even leading term would lead you to the same end behavior at both ends. Okay. If it's odd degree, the end behavior will be opposite. The other thing is, how many zeros do you have? You have 1, 2, 3 zeros, right? So you know the degree is at least 3 because the only way you get to 3 zeros is to have 3 linear factors. Okay. Now actually you got 4 because you got this one twice. That's it. And a lot of you nod your heads as complete recognition. Okay. If you don't have complete recognition of that, review it. Okay. Multiplicity tells you how many times that zero counts, tells me how many times you've got that linear factor. Okay. And the number of turning points, well, how many turning points do I have on this thing? I turn here, I turn here, and I turn here. 3 turning points, right? It's n minus 1, where n is the degree. And doesn't have to be n minus 1. It can't be greater than n minus 1. Okay. in order to turn once, you have to have like a quadratic, which has two linear factors. Okay. If you want to turn twice, you better have the third degree because you need three linear factors. You have three zeros, so you have to make a couple of turns. It comes down to that. It's a little more complicated than what I said, but if you've got that much, just read the book and remind yourself of the finer points. Okay, or be content to go in without the finer points. Might cost you a letter grade, especially trying to make an A. Okay, but it's not going to kill you. So now I want you to do the best you can because you got lives and you got other courses. Prepare as best you can. But get at least these basics down, come in with these basics, and you should be okay. All right. Okay, now factor polynomial of degree greater than 2. Find a 0. I say good luck with that. Because if it's a real world polynomial, there's almost zero chance you're going to be able to find a 0. Except by graphing it and estimating and bypassing anything but what a machine will tell you. Okay. But if you can find a 0, okay, I'll say find a 0 and call the 0 z, then divide by x minus z. Polynomial. Now, x minus z multiplied by the quotient. Okay. And then repeat. As necessary. If possible. So the latest quotient is quadratic. Then factor the quadratic if possible. Okay. There it is. Usually doesn't work, but on a test, if I ask you to factor a third degree polynomial, fourth degree polynomial, there's a good chance it's going to work. Okay. use the quadratic formula if necessary. You can always leave it the solution. I was going to say about that. Hang on. I thought it was worth saying. But so if polynomial is not in factored form, polynomial is not in factored form, do your best. But most of the polynomials I'll give you will be in factored form. There'll probably be something that asks you, oh yeah, the other thing I was going to say about factoring these things. Pi to 0. Pi z equals plus or minus 1, plus or minus 2, plus or minus 3. And that means just plug it into the polynomial and see if it gives you 0. Probably going to be most of third degree polynomials, so the cubes of these numbers won't be over 27. Okay, so you're not going to have huge numbers to worry about. Now, there are other tricks that we aren't going to cover here. Rational zeros and stuff like that. Because again, they're of theoretical importance, but they're of very little practical importance. And if you ever need to use those ideas, you'll be in a higher level course where those ideas are going to be really easy to. Okay. So I make the decision to concentrate on the really fundamental stuff. Although that other stuff is really neat, I'd love to do it. There are other things you're going to profit from more than that. And again, if you ever do need it, it's going to be in a more advanced course, and you'll be more mathematically sophisticated. It'll be easy enough. Okay, I'm going to pause this thing just to see if it's still working. Okay, I've got 3 zeros. Okay, and let's say this is a 0. From a factor x minus a. Okay. If it's a factor x minus a, that's linear. So it's going to go through this thing in a straight line, whether it's up or down. Okay. Say this is 0 from x minus b squared. It's going to be hard to read. It says linear straight line. This says quadratic. It's a parabola because you know that x minus b squared is going to have a parabolic graph. Okay. It's just shifted b units from the toolkit function. Okay. And then over here, let's say we've got a 0. x minus c quantity cubed. It's like y equals x cubed as it goes through there. What I'm saying is it's like that word is near and it's all missed. Like y equals x cubed behaves near x equals 0. And what that means is you could have this behavior. Okay. Now, the x cubed function comes from the left and goes up, right? Of course, you could have a negative factor here. Okay. It depends on what else is in the polynomial, whether it's going to be going up or down as you go through here. So that's like your x cubed function. This is like your x squared function. So let's say it looks like this. And this is like a linear function. Well, might look like this, okay? Near the 0. So I'll just kind of draw these in blue. And now I'll do polynomial. Okay, well, if these are the only zeros, then I know the thing starts up here because it can't get, first place it has to go through the x-axis is here, and it has to go through like this. And then I'm going to have to turn around, come back up through here, and then we're really kind of in trouble because we can't get around to do this. Okay. So I'm going to say, well, I thought maybe that we had a negative coefficient here. When I first thought about it, but I lost the negative sign. Maybe it really looks like maybe it really looks like this. Okay. So now I can draw the function. Come down from up here. Then come down here. Well, really want to draw it right. Except for that little segment there. And then I'm going to turn around, come up here. Then I'm going to come down here and turn around, come up to here, and then come on up. Okay, so this could be a polynomial. If x equals some number times x minus a times x minus b squared times x minus c cubed. Where the coordinate here is a0, coordinate here is b0, the coordinate here is c0. That answer your question? That help clarify it a little bit? Okay. So if you have an even numbered power, it's going to kind of look like a parabola, but I've said many times, as the power gets bigger, the parabola gets flatter. Okay. If it's an odd power, well, it's either 1, in which case we go straight through, or it's at least 3, in which case it looks like this, but a lot steeper and flatter if you got 5, 7, 9, or whatever the power. Okay. Okay, good question. got a pair of points here. If I do a difference quotient or a fundamental triangle, I'm gonna get a slope, right? Now, if I give you this function, tell you what A, B, and C are, and whatever, give you the rest of the function, and I tell you what this X value is and this X value. So let's say this is X, and this is X plus H. These two vertical lines. If I give you numbers for X and H, are you going to be able to figure out the coordinates of these points? Well, if you got the function and I give you the coordinate X, give you a number for X, you plug it in, you're going to get this coordinate, okay? Then if I give you a number for H as well, then you can figure out X plus H, and you can get this coordinate. Okay, and then you can sketch a fundamental triangle, label the rise, the run, and get the slope. Or just calculate it, depending whether I ask you to show the fundamental triangle or not. That should be easy. Again, you have all the numbers here, so you can always evaluate this function, plug in numbers, okay? And then I give you a number for X and a number for H, and you can find the slope, okay? You could do the same thing for this pair of points. Or this pair of points here. Okay. Now, where's the slope steepest? Which slope segment is steepest of these three? This one, or this one? Vote. How many think this one? How many think this one? How many think this one? Okay. Well, the vote goes for this one, and yeah, it's steeper here than it is here. Okay. And it's steeper here. It's pretty steep. It's steeper here than it is here. Okay. If this is a hillside and you're trying to walk down it, well, you're not going to walk down that. That's really a cliff. Okay. You wouldn't have any trouble walking down this. Okay. You might be able to walk up this. If that's a roof, could I walk it? Probably could, but I wouldn't want to because it's right at the corner line. Okay. When I was younger, I might have risked it. It's a little too steep to walk on safely. And maybe too steep to walk on, period. A little steeper than that, you could walk on. Does that make sense? Okay. Where's the slope least? Well, right here. Could you show me 2 points where the slope would be 0? I can show you 2 points on the graph where the slope would be 0. How about here and here? Okay. Now we could have done it down here, but I've already drawn a lot of points around here. There's a point here where the slope is 0, right? Now what's going to happen to the slope here? If I have a point here and a point here, I'll get my fundamental triangle, my slope. If I have 2 points here, I get a fundamental triangle. Which one do you think is going to be steeper? This graph gets steeper and steeper. After you leave the zeros, it keeps getting steeper and steeper. Okay, positive power functions have that characteristic if the power is greater than 1. Okay. So I could well ask you after you've done a graph, maybe you're given the function, maybe you have to find the function from the graph. I could well ask you questions about how the difference quotient behaves. Okay, that would be a really good thing for you to be able to do as preparation for a calculus course. Give you a lot of insight that you probably wouldn't otherwise have, even if you take any calculus course. Okay. And I'm assuming that everybody in here is on track to take calculus. Not everybody is, but it's a pre-calculus course. So we're going to talk a little bit about these concepts because they're good whether you are going to do calculus or not. Okay. They're especially advantageous for calculus, but it gives you insight into the behavior of these functions. And that can be important no matter what you're going to do. Okay. And it's not hard. If I pose a problem like that, I'll be pretty explicit in the way I phrase it. Fair enough?